So let's move on. Good. So we talked about universal gates for classical computing. So what about universal gates for quantum computation? So what about Toffoli? Can I say that maybe the Toffoli gate is universal? What do you think for quantum now? So what the question was, why can't Toffoli be considered a universal gate for quantum quantum computation? And the answer is exactly what he said, that basically I want to be able to generate arbitrary unitary matrices, and the Toffoli matrix will not let me do that. In particular, the Toffoli matrix is just a permutation matrix. Okay, so it cannot even implement the Hadamard transform, for instance. So it doesn't work. So what's our next candidate? So if Toffoli cannot do it by itself, whose help should it seek? Hadamard, yes. So can this be, can this set be universal? Everyone knows what universal means, right? So basically any circuit I should be able to express just using these gates. So again, in fact, the answer is no, and this is because of phase shifts, for instance, right? So this was the answer to one of the questions from the feedback yesterday, that what are these phase shift operations useful for? So the answer here is that Toffoli and H only map real to real, right? So things like phase shifts and other complex transformations can't be captured, and it will turn out that actually Toffoli or C naught, either one of them, together with Hadamard and this phase shift operator, this phase shift unitary, is actually universal for quantum. Okay, so I am not going to prove this, I am just going to state it as it is. Is it fine? So now we are about to discuss something really exciting. Okay, so first of all, we will try to get our hands on this quantum parallelism that we keep waving our hands around. Let's try to finally write it down a little bit formally. So first I want to say that there are two ways in which we can think of maybe it's really the same way, but I am thinking of parallelizing inputs and outputs. Okay, so obviously I can't parallelize outputs if I don't parallelize inputs, but let me try to generate a interesting superposition as my input, right? So of course for like a single qubit, what is the first thing that comes to your mind, like for an interesting superposition? As the input qubit, what is the first qubit that comes to mind which is interesting and not classical? So something which is like a sort of parallelization, or in the case of a single qubit, just a superposition, just the plus, right? So very good. So that's exactly what I had in mind. So for single qubit, just the plus seems like a nice, interesting new thing that I can compute with, and actually applying the Hadamard to multiple zeros and getting the product of multiple of these pluses will give us something very interesting. Okay, so let's see how that will look. So if I have 0 here, okay, and Hadamard, okay, and another 0 and Hadamard, so what do I get? I get plus plus, right? And what is this plus tensor plus? So it's 1 over root 2, 0 plus half, right? 1 over root 2, sorry, 0 plus 1, 1 over root 2, 0 plus 1. So this is half, right? 0 0 plus 0 1 plus 1 0 plus 1 1, right? So we already, even in the case of dimension 2, we were able to get a superposition over all the basis states by applying the tensored Hadamard transform, and this generalizes to n bits. Okay, so if I apply, you know, the Hadamard, the tensored Hadamard to 0 to the n, right, what I get is 1 over 2 to the n by 2 summation over all possible x. So I can get this. Okay, so this is already cool. I mean, this is important because well, first of all, it's important because it's interesting, at least to me. Secondly, it's important because we'll be doing this a lot. So most of our quantum algorithms at some point or the other will require us to apply the Hadamard to you know, the all zero string and get this nice superposition. It's very intuitive, right? I mean, I want to do something beyond classical, so obviously I want to move to superpositions and so on and do things there, right? So that's all. So this is nice. So now I want to actually compute functions, right? So this is what, this is just, I mean, fine, I took the zero string and I generated a superposition over all input states. Now I want to actually compute a function. So far I have been developing all this theory about, you know, how to compute classical functions and so on. So let's put that to some use, right? So now what I would like to do is I would like to generate a superposition of function outputs. So instead of just generating, you know, a superposition of x, I'd like to generate a superposition of x f of x. Okay, and this is actually, when I managed to do that, this is already something which is much beyond what I could do before, and we'll see that in some cases, you know, if I measure and I okay, we'll see that when we get to it, because it will only be confusing if I say it now. So we'll see that doing that will be very useful to us in many quantum algorithms. Okay, so let's try to do that now. So the idea is this, right? So maybe again I'll start with you know, just a single bit. Okay, so what I would like to do now is that, you know, I have my function. So I am giving you a blank register, right, this 0 over here, and I give you this. So what is this psi? So at this point here, right, let me call this phi. So what is phi? It's nothing but this, right? So basically I just showed you in the previous slide that, you know, I'll over here I'll get the plus state, right, and that tensored with 0 is what I've written down. Is it clear to everyone? Okay, so this is nothing, it's just basically by definition of Hadamard, this is what I got, right? And now what was my CF doing? If you remember, you know, it was taking an x and a y and it was outputting f of x and y XOR f of x, right? In this case our y is 0. So y XOR f of x is simply f of x. So this is going to output x, right, and f of x, right? So what is our x here? It's whatever is going inside the function box. Maybe I'll write down all the steps because I don't know, maybe this is going too fast. So let's see. Okay, so if I don't want to call this x. Yeah, so if I consider this simpler circuit, okay, so let me consider a simpler circuit of x, y, x and y XOR fx, right. So now I am saying that if x is 0, then we get on the second wire we get y XOR f of 0, right, and if y is 0, then I get basically f of 0. Everyone agrees, right? Similarly, if x is equal to 1 and y is equal to 0, then I get f of 1. Does everyone agree with this? Okay, so by linearity, okay, if x is plus, which is what I was doing in the previous circuit, then I get zero f0 plus 1 f1 by root 2. Does everyone see this? Right, because when x is 0, I get 0 comma f of 0. When x is 1, I get 1 comma f of 1, right. So by linearity, when x is 0 plus 1 over root 2, I get 0 f0 plus 1 f1 over root 2. Okay, and this is really, I mean, I want to say that this is really a remarkable state. Right, I got a state which is actually a superposition of function values on many different inputs. So this I feel is like the first illustration of how this quantum parallelism that we have been talking in a hand wavy way about so far, right. This is the first illustration of making it in some way concrete, right. Just using the little bit of notation that we have set up so far, we are able to now generate this amazing state, right. There was no way for us to do this before, right. And now how to extract something out of it and so on, of course, we still have some battles, but this is already something that we really did not know how to do before. Okay, so what we showed is that if I maybe I'll draw it over here, that if I apply this function, if I invoke this function oracle with the plus and the 0 state, right, then I get this I get this. And this is something that I'd like you all to sort of play with and familiarize yourselves with, like what do I get if I put different inputs on these wires, then what are the outputs that I get. Any questions? So one of the other just finishing up this discussion. So this is for 2 bits. Of course, I can generalize this to n bits. So for the case of n bits, what happens? Okay, so here I will prepare an n plus 1 qubit state. Zero tensor n 0. Okay. Note that that is what we were doing over here, right. So here n was 1 and there was a 0 here. Okay, so 0 tensor n 0, and then what will I do next? I will apply the Hadamard on the first n bits. Right, I will apply it on the first n bits, and then I will apply the quantum circuit that is implementing the circuit F, right, the quantum circuit implementing F. And what will this give me? So, it will give me 1 over 2 to the n over 2 x 0 1 to the n x f of x. Okay. So, this is the generalization on n bits, and this is, as I already said, already very cool, because we never knew how to do something like this before, right. But extracting something new out of this is going to be all the creativity in quantum algorithms. So, it turns out actually we will talk about this more as we dive deeper into these algorithms. There are basically a few tricks that the algorithms, at least the algorithms that I have seen and that you will see in this course, they all use a few tricks. And basically this idea of applying the Hadamard transform is going to show up again and again in various places, because as we will see, this Hadamard transform is actually implementing a Fourier transform. Okay, so we will define all of this properly, but I just want to give you a little bit of intuition that essentially this Hadamard transform ends up being so important because it allows us to change the basis of whatever is input to it. And when I manage to do this change of basis, then it turns out that some interesting patterns emerge. So, when I do a measurement finally, right, I get some one state, right, and which state do I get? I get the state with the highest which has the highest probability associated with it, and this gives me information about what patterns are there in this data. So, essentially the quantum parallelism is giving me like a very, you can think of it as like a very large amount of data, right, exponentially many threads are sort of somehow living in this quantum state. And by applying Fourier transforms in clever ways, and of course depending on the algorithm doing things around it, I will be able to learn, by applying Fourier and by applying the Hadamard transform and doing various things around it and finally measuring, I will be able to learn some patterns in this large data, which I could not have learned in the classical setting without doing exponential time computation. Basically that is what is going to happen. So, it is not as though it's completely as I said trivializing classical algorithms, because how to measure in a way, like what computation to do so that a measurement gives me something useful, this is going to be non-trivial. But it will turn out that for various problems, especially problems with a lot of structure. So, actually this is why poor old crypto gets broken, because we end up using problems that have a lot of structure to build cryptography. This is unsurprising because we want cryptography to give us some kind of functionality, and you need some algebraic structure to get some functionality. Okay, so typically we need some computational hardness assumption saying that even though there is this structure, it is indistinguishable from random. There is some such conjecture which is made. By the way, please ask me questions. Is this making sense? I am trying to give an intuition as to why cryptography problems end up being a very natural target for quantum computers. So, especially folks who have not studied much cryptography before, if this is not clear, please please ask questions. Okay, so what I was saying is that we will see a little bit of some problems that are used in cryptography. Of course, we will not see too many that are broken by quantum. We will actually see discrete log and factoring, for instance. Maybe that those are good enough examples. So, we will see that these problems are broken by quantum. What we may or may not see depending on time is how these problems were used to give us interesting cryptography. So, if time permits, I will definitely show you some of that. So, basically how does this all come together, right? The point I am trying to make is that cryptography relies on problems that have structure, mathematical problems that have structure, but classical computers do not know how to solve except by doing some kind of exponential brute force stuff. Okay, cryptography relies on these problems, and quantum computers are exactly very well suited to attack problems which have this kind of structure, because like I said, using this very high level recipe of using Hadamard to change basis from whatever to perform the Fourier transform to change basis and so on, we will be able to find patterns that give us some information about the underlying structure. Okay, so maybe this is a little too abstract at this point, so I will stop now. Nevertheless, I would like you to keep this intuition in mind, because really what are we trying to do via this course, right? We are trying to understand the relation of quantum algorithms with cryptography. That is the title of the course. So, the point is that trying to look at problems that are used for cryptography, trying to look at tools and techniques that have been developed for quantum algorithms, finding which ones work, and then trying to predict problems where they will not work. This is sort of the higher level goal of studying this, right? So, in the next few classes we will see that. So, I am almost out of time, I will stop here.